Hey all, this is Derek, and this is 7.1, Graphs of Polynomial Functions. So we start with some definitions and just a little bit of terminology involving polynomials. So first off, a polynomial has the form of this very formal thing that's written out in the notes. I wrote out the first term a little bit larger, so it goes a sub n x to the n. And then where the coefficients are real numbers, so that's these values in front. And n is a non-negative integer, so n is going to be our power or exponent. So the degree of a polynomial is the largest power n, so that whatever is the largest power, that's going to be called the degree. The leading coefficient is a sub n, that's this right here. So again, in the first term, it turns out the power and then the leading coefficient end up being pretty important in terms of what the function will do overall. And then the maximum number of zeros equals the degree of the polynomial. So zeros are the places where you are crossing the x-axis. So if we think of x squared, this would be degree 2, and it has at most 2 zeros. So the maximum number of zeros in this case would be 2. I can draw this so it only has 1 zero, and likewise I can draw it so it has no zeros. So this is again a maximum. Sorry, I'm getting tail bumped by a cat here. This is actually the second try of shooting this video, and the other two cats have already had appearances in the first one. Okay, Agatha, there we go. Where was I? Okay, so we were saying x squared, it's degree 2, so it can have at most 2 real zeros. And then the maximum number of turning points equals n minus 1, or 1 less than the degree of the polynomial. So here we are with x squared, 1 less than the degree would be 1, and what that is the vertex. So turning point is like all the little, like a vertex for a parabola, where the slope in this case was negative. It has to pass through 0 and then is positive. So it was decreasing, 0 increasing. So when it does that, when it changes directions, that's called a turning point. And it could happen, opening down or opening up, either way. And so again, the maximum number of turning points is 1 less than the degree. So since this is degree 2, it can only have 1 turning point. If it's a cubic, degree 3, it could have 1, 2 turning points and so forth. So what that will look like in a couple of questions, it actually takes, there's cattail again. It actually takes way less time to do the questions than to describe the definitions. Yeah, Aggie, that's really irritating. So find the degree, leading coefficient, and maximum number of real zeros of the polynomial. So to do all of that, what I basically need to know is what's going on with that first term. So our first term is 7x to the 5th. And so our degree is 5. Our leading coefficient is -7. And then the maximum number of real zeros is the same thing as the degree. That's how many times it can cross the x-axis. And so that would be 5. For this next one, determine the least possible degree of the polynomial function. So however many turning points I have to have one more than that for the degree. I could have more than that. So if, like, for instance, if I have x to the 4th, it ends up looking like x squared. So x to the 4th could have 3 turning points, but it only has 1. This case, we have 1, 2, 3, 4, 5. So while there could be more, this has at least 6, which is the number of turning points plus 1. So here this is at least degree 6. And that said, this thing is basically going on for, Agatha, you were just not being helpful. Thank you. This thing is basically looking like an x squared, right? So it could be x to the 8th, it could be x to the 10th, it could be any even power, but it has to be at least 6. Okay, so this one is asking us to determine whether the function is a polynomial. If so, find the degree. So this is a polynomial. It's a really sneaky one. This would be 11x to the 0. Remember, when we have a 0 power, that's like saying something is just a 1. And so it's the least interesting polynomial ever, but it is a polynomial because this is not imaginary, and this can be 0, 1, 2, 3, 4, 5, and it's 0. So that would be yes, and we would say it's degree, degree 0. This root makes that not a polynomial because that's the same thing as having negative x to the 1/2. We can't have fractional exponents, so that's just a no. This is a no because it's a fraction, so we can't have the exponents in the denominator. And then even if I rewrite it in the numerator, now it's negative, which was the other thing we couldn't have. It has to be 0, 1, 2, 3, 4, 5, etc. So that is a no. And then this one's just totally normal. The degree would be 6 because that's our largest power. So this is yes, and then degree 6. Okay, next up is what's called end behavior for power functions. The power function takes this form as basically just the leading term of a polynomial. And I'll write this a little bit bigger. F of x equals k x to the n. So this pretty much has two features, right? It has k and it has n. K can either be positive or negative, and n can either be an n-zer power or degree. N can either be even or odd. And that's all the things that can happen in terms of what this thing will look like. So if we think about an even power, an easy one would be x squared. That is even with a positive coefficient, it's 1, and that one opens up. So as x goes to negative infinity, this goes to positive infinity. As x goes to positive infinity, f of x or the y's also go to positive infinity. And so basically everything that has these features, positive, even, is going to, if we zoom out far enough, look like x squared. X cubed will be our next one. So that one, positive coefficient, odd power. So that one, it decreases as we go to the left and then is increasing or going to infinity as we go to the right. And then we have basically their reflections. So if it's negative and even, that's like a negative x squared. So it's all the graphs are going to look like negative x squared and have this behavior where they both go to negative infinity. And likewise, if I reflect x cubed, negative x cubed, then it's this one will be decreasing, so decreasing left to right, or it's going to positive infinity on the left and negative infinity on the right. What we can do with that is look at any polynomial function and determine what the graph is going to look like, at least big picture, by examining the leading term. So state the end behavior of the function. Okay, so for this one, I'm actually going to start on B because it's easier, and I'll loop back here. This one is the only example where we can actually see what the leading term is. These other ones we have to do just the one step to figure it out. But this one is negative and even, because that's negative 7x to the 4th. So negative even things are going to look like that if we zoom back far enough. So as x goes to negative infinity is how this reads. X goes to negative infinity. F of x, which is like the y's, are going to negative infinity. And as x goes to positive infinity, the y's are still going to negative infinity. So looking at a function, a polynomial function, we can know what its end behavior will be based on that leading term. Same thing for these other four, except these ones are in some version of factored form. So here you can see if I multiplied this, I would get 5x to the 5th. And this is positive odd. And so positive odd things look like x cubed. And so that's all you're trying to do is match it to one of those four graphs. So as x goes to negative infinity, this is going to negative infinity. And likewise, as x goes to positive infinity, this is going to positive infinity. Here, these last two, they're factored. And if you think about, if I had something like, x plus 1, x plus 1, x plus 1, for instance, and I multiply these out, I'd get an x squared and 2x plus 1. And then multiply that, and I end up with x cubed and a bunch of stuff. So rather than doing all that, I'm just going to count my x's. I'm going to go, I got 1, 2, 3 x's, which means if I do my FOIL, it's going to count x cubed. So I can just count the x's rather than actually have to do the multiplication. So much easier to do it that way. So right here we got 1, 2, and then that's squared, so 3, 4 x's. So this, if we did FOIL it out, would come out x to the 4th, which is positive even, so both are going to go to positive infinity. There we got that negative sign in front, 2, and then I got 1, 2, 3, 4, 5 x's. And the fact that that's a 2 doesn't really matter. It just means it's stretched a little bit. The important thing is the negative and the odd power. And so negative odds, those look like that. So as we go to negative infinity, it was going out to positive infinity, and then positive infinity goes to negative. Okay, so this chart makes up half of what we have to know to be able to graph one of these. And this next piece, x-intercepts and multiplicity, that's going to give us kind of the other half of the picture. This gives us the end behavior. This is going to tell us what's happening as we're going out to large numbers. Multiplicity and intercepts, that's going to tell us what's happening in the middle of the graph. So to find an x-intercept or zero, same thing, right? X-intercepts and zeros are interchangeable terms. A polynomial, set y, which is also f of x, to 0 and solve. So basically to find our zeros, we're going to let y equal 0 solve for x. Find the y-intercept. I don't think we actually end up doing that too much in this version, but if we needed to find the y-intercept of a polynomial, set x to 0 and solve. I mostly don't do this because when we're graphing these on paper, that could be like a really huge number, so I kind of ignore the y-scale most of the time and pay attention to the behavior, because that's what ends up being important. More on that to come. Multiplicities. So multiplicities are the power that the zeros, or the x-intercepts, are raised to. The sum of the multiplicities is the degree of the polynomial. That's actually what I was just doing on that last page, is I was adding up the powers. So the powers are like the multiplicities, and then that gives me my degree. So I have an example here just to kind of talk through all the terminology here. So we have f of x equals x plus 3 to the 4th, and then x minus 2 to the 5th. So this has a 0, or an x-intercept, at x equals negative 3. And that would be multiplicity 4, because that's to the 4th power. And then this has a 0 at 2, because this is x equals 2. And that is multiplicity 5, because that's to the 5th power. So here's the important thing in terms of graphing. Even multiplicities are going to bounce in the same way that x squared does. If we think about a graph of x squared, it comes down, it touches or bounces off of that 0, and then comes back up. And then odd multiplicities, they're going to cross the same way x cubed does. So this is what I mean by bounce or touch. Some books use one word, some books use the other. And this is what I mean by cross. So here, right, there's a turning point. It's turning directions. This one is passing through. And that's going to be true anytime we see, so like here, this to the 4th power, this would be a bounce, this to the 5th power, that would be a cross. So what that's going to do is give us a lot of information about what's happening in the middle part of the graph. So for these next examples, we are asked to find the zeros that give the multiplicity of each, list the zeros in order from least to greatest. So I'll manage to do that probably on this first one, and then I will fail miserably for the rest of them. That said, when you're entering them into the computer, watch out for those directions so that you get them in the same order that the computer is programmed to take the answers. So for this first one, find the zeros and give the multiplicity of each. So our zeros are going to be x equals 3, x equals 4, and x equals negative 4. So for putting that in the computer, I think it has boxes. So you'd have to go negative 4 first, 3 in the next box, and then 4 in the box after that. So these would be the zeros, and it's just the program for that version. Likewise, if it was given as a list, you would just do it as a list. And then we're asked to find the multiplicity, so then I think the multiplicity is in the next box. So for negative 4, that one is multiplicity 2. For positive 4, that one is multiplicity 2. And then for 3, that one would be multiplicity 1. These next couple examples, so here they're messing with us a tiny bit. If I finish factoring that, I'll write this one bigger so you can see. We're looking for two things that multiply to 25 and add to 10. So that would be x plus 5. And then you may end up writing that as x plus 5. So if you do that, you're kind of hiding the fact that that's multiplicity 2, which is then really easy to miss. So this would go 2x minus 7 to the 5th, x plus 5 squared. And that helps me recognize two factors, so multiplicity 2. This one, if we set it equal to 0, bring over the 7, divide the 2, you'll get x equals 7/2, and that would be multiplicity 5. And then this one would be x equals -5. So if you're doing a list, that would come first, multiplicity 2. This example, so here we are not factored, so we would need to do that. So 10x cubed appears to be my common factor, and that's going to leave me x squared plus 2x plus 1 right there. And then this is another one of those trinomial squares, like this one multiplies to 1, adds to be 2, would be x plus 1, x plus 1. So I'll write that as 10x cubed and then x plus 1 squared. So this is x equals 0, would be that one, and that's multiplicity 3. X equals -1, and then multiplicity 2. Okay, for number 6, use the graph to identify the zeros in multiplicity. Assume all zeros are either 1 or 2. Order your zeros from least to greatest. Okay, so for zeros, I'll just start a list here and then do the multiplicity to the side. Okay, more cat bombing. Come on, thank you. So we have x equals -1. There's 1 0. X equals 0, and then might as well do multiplicities as I go. So this will be my zeros and my multiplicities. So this one is crossing through, so it would have to be to the first, assuming all are either 1 or 0. This one is again crossing through, so that would be 1. X equals 2 is my next one. That has to be multiplicity 2, because you see how it's coming down and bouncing. Likewise here on 4. That will also be multiplicity 2 because it's bouncing. Okay, so let's try this with an example. Let me go through the steps first. So first thing we're going to do is figure out the end behavior, and then to do that, if the function is already factored like this one, we're going to add up the powers to figure out the leading term. If the function isn't factored, then we just get to use the leading term. So this one is factored, so I'll just count up. I got a negative there. I'll write -5. Again, the 5 is not super important, but it's there. So -5, x squared, and this would be, so 1, 2, and then 3, 4, 5 x's. So -5x to the 5th. So this is negative and odd. So that's going to be my general shape. When I go to draw my graph, I'm going to start at the top. And if I do everything right in the middle, it should come back out this end. And then next I'm going to find my x and y intercept. I'm actually going to not have you find the y-intercept because, again, the scale on the graph can end up being really huge and confusing. And that's kind of not our goal in this. We're just trying to get the general shape. And that you'll see in the next section, again, useful for inequalities and in calculus, that general shape, we end up with much, much better ways of figuring out turning points and such. So in this course, we're really focused on just kind of getting the lay of the land, so to speak. So here we're going to have x-intercepts of x equals 0 and x equals 3 and x equals -4. And then determine the bounce across behavior. So this one is multiplicity 2, that's an even power, so this one's going to bounce. 3 is also multiplicity 2, so that's going to bounce. 4, that's to the first, so that is an odd power, and so that one is going to cross. I'm going to throw my intercepts on here, so we got 0, -4, and 3. And so I know what I'm supposed to do at each of these intercepts, and then from the end behavior, I know which way to come in, which way to go out. So my graph should start at the top. This says go through -4 and cross there. And then I have to come back and hit this. So somewhere down here, there's a turning point. And at 0, I am supposed to bounce. And at 3, I'm supposed to bounce again. And so my graph is going out the right way. And there's all the behavior at the intercepts. If we were in class, someone would ask me how I know how high to draw or low to draw these turning points. And I would say the answer to that is Calculus 1. Calculus 1 is all about finding those points. And so that's why I was saying in this course, I'm not going to worry about the Y scale because the tools we have at this time absolutely suck for doing this, and this is exactly what calc is for. So I'll hold off kind of the y-intercept and worrying about the scale on it for that next class. Okay, same thing with a couple other examples. So for this one, our end behavior, this is 1, 2, 3, 4 x's. There's a negative in front, so it'd be negative x to the fourth. So that is negative and even, so it should open down like that. Our zeros are x equals 0, it's to the first, so it's going to cross. X equals 5, it's to second, so it's going to bounce. X equals negative 2, and it is to the first, so it is going to cross. And I'll get those labeled on here, 5, negative 2. So this is going to come in from the bottom. It is going to cross on negative 2, and then we're going to come back and we're going to cross on 0, and then we're going to come back and we are going to bounce off of 5. And if you look, if you kind of zoom back, it has this same basic shape. And again, the zeros here are telling you sort of what's happening in the middle, and behavior is telling you what happens as you go to infinity. This one, so it's x to the fourth, so it's going to look like this because it's positive even, but this time it's not factored, so I have to do the work to get the intercepts. So it looks like I can take a common x squared out of all those terms, and I end up x squared plus 9x plus 18, and then that would be x squared, x plus 3, x plus 6, multiplies to 18, adds to 9. So x equals 0 with a bounce, x equals negative 3 with a cross, and then negative 6 and cross. So there's my intercepts. I'd be starting from the top, crossing on the 6, I am crossing on the 3, and I am bouncing off of the 0. The cats are very active for this video, sorry. Okay, so for this last one, I just wrote it a little bit bigger here. We have to do a little bit of factoring. It's an x cubed, so we know it's going to look like this. And this is a 4-term factoring, so I'm going to do grouping. So let me set this to 0 because I am actually solving for the x-intercepts. So we'll take an x squared out of those first two and get an x plus 1 there. And then we're going to take a negative 16 out of those next two so that we get that matching x plus 1. Remember, this is our factor by grouping. Taking this out front, I end up with x plus 1, x squared minus 16, and then that's our difference of squares. X plus 4 and x minus 4. So we end up with x equals negative 1, negative 4, and 4. And then these are all going to cross because they're all to the first power up there. So we got negative 4, negative 1, and positive 4. Starting from the bottom, this is going to do something like this. Oh, here's a good example of why I'm ignoring the y-intercept. On this one, if I let all those x's be 0, this one would be negative 16, so I'm like way off the graph down here already. And so that's why, again, we're looking really at these more for the behavior. Let's see if that... Oh, the cats are being awful today. Anyhow, we're looking at these more for the behavior rather than the particular points. Again, calculus will help us find those, and we can find that if we wanted. It's just not necessary for what our goals are. Okay, so for these last couple examples, we're going to find the equation giving either a graph or a verbal description, like in this case. So find an equation with a solution of x equals negative 2 multiplicity 1 and a solution of x equals 3 multiplicity 2. And then they're giving us the y-intercept, and I'll show you how come here in just a second. So we're going to have y equals, X equals -2 means I must have had a factor of x plus 2. Otherwise, I can't get that. Multiplicity 1, so there'd be like an invisible 1 right there. And the solution of x equals 3, that can only happen if I had a factor of x minus 3, multiplicity 2. So that's right there. The reason they're giving us this intercept is that stretch factor. So there are an infinite number of... Okay, the dog is now visiting this time. Like, this video is cursed. The reason we're given the y-intercept is so that we can figure out the stretch factor. And I think we saw this back when we did parabolas. So I'm going to let this be a, and then we know when x is 0, y is 36. So you can say a, 0 plus 2, 0 minus 3. So a, this would be 2 times 9, which would be 18. Then dividing the 18 on both sides, we get a equals 2. So our equation would look like y equals 2, x plus 2, x minus 3 squared. Okay, on this last example, we're given a graph and then again asked to find the equation. And here we're assuming multiplicity 2 if it bounces and multiplicity 1 if it crosses. So right there we have, that would have to be x plus, let me leave myself some room there, y equals a, and then x plus 2, and that would be multiplicity 2 because of the bounce. Then we have to have an x minus 1 to get that 1. It'd be the first because it's crossing. And likewise an x minus 4, and also crossing to the first. This here is 0, 2, so that gives us a point that we can use to find that stretch factor. So y is 2 when the x's are 0, so this would be 2 squared would be 4, negative and negative make positive 4, or 2 equals 16a, and then dividing the 16 over 1/8 equals a. So final would be y equals 1/8 x plus 2 squared, x minus 1, x minus 4.